Okay, welcome to another video on 5 of the best AQA multiple choice questions. This time the topic is waves. Alright, so again, pause video to read each question separately, then have a go. So, question number 1. 2 points in a progressive wave are 1/8 of a wavelength apart. So let's imagine we have a wave. One full wave would be from there to about there. That's one full wave. And it says 1/8 of a wave apart. So cut it in half, that's half of a wave apart, that's a quarter of a wave apart, that's 1/8 of a wave apart. Okay, that distance there is 1/8 of a wave, and it tells me that that is 0.5 meters. So that means to go from there to there would be 1 meter. So a half of a wave, this much, is 1 meter. A half of a half. Right, so a quarter of a wave is 1 meter. So another quarter, and another quarter will add up to 4 meters. Right, so we've got a 4 meter long wave oscillating at 10 hertz. What's the minimum speed of the wave? V equals F lambda. 10 is the frequency, lambda is 4. So this gives us 40 meters per second. So I'm going to go with D. Okay, this bit was a bit tough, to be fair. Next question, which of the following waves cannot be polarized? Cannot be polarized. Right, so polarization is a wave that oscillates like this. If you put slits in front of it like this, the wave won't get through. But if the slits had been placed in this orientation instead, the wave would have made it through. So waves that are transverse can be polarized. Only transverse waves can be polarized. Right. So radio waves, they are transverse. So they can be. Ultrasonic waves, let's come back to the one. Microwaves, again, another type of electromagnetic waves, they are transverse. Ultraviolet, another type of EM wave, they are ultraviolet. Well, ultrasonic, they aren't waves that oscillate up and down if this is the direction of movement. They are waves that, if this is the direction of movement, they oscillate backwards and forwards like this. So you have compressions and rarefications in air. I'm just representing it here as lines, but the idea being that you've got compressions, you've got something vibrating like a tuning fork, vibrates backwards and forwards, smacks into the air, you get compressions, you get rarefications spreading out. So this would be compressions, this would be rarefications spreading out from the source, and putting lines in front of it like this, a grid would not make any difference. Either way, the direction of that grid would make no difference. So only transverse waves can be polarized. So that's the understanding for why B is the correct answer. Right, next question. We'll skip to the question and read it first. So pause video, read question. Diffraction pattern is formed by passing monochromatic light through a single slit. If the width of the slit is reduced, which of the following is true? Well, this is the setup then. You've got some kind of light source, so it could be a laser here. It says it's monochromatic, so yeah, laser's a good choice. It's got laser coming out here. You've got a single slit, okay. Let's move that slit down a bit. You've got a single slit, and what you're going to get is you're going to get diffraction happening here. So you can either think of that as being like this, right? And that reaches a screen. And on the screen you're going to get a bright spot in the center, dark spots, and then subsequent bright spots further away. In fact, right, whenever you get single slit diffraction, you get large central maxima followed by subsequent smaller ones. So you get a large, bright, and wide central spot, and then the subsidiary ones are less wide. In fact, they're half the width of this one. Right, so this is just generally about single slit diffraction. But how are we going to know what happens when you make this smaller? Okay, if you make this gap smaller. Well, how does diffraction happen fundamentally? Diffraction happens because light travelling, say, from this point and light travelling from, say, this point are both travelling the same distance. The path difference is identical, right? Therefore, when the waves arrive here, they're going to arrive and they're going to constructively interfere, forming a bright spot. Now, if you go further out, say to here, where you've got this dark spot, right, draw it again down here because it's getting a bit messy, right? So if you was to go out to where there's a dark spot, right, that means that there's a difference in path. If this is path A and path B must be half a wavelength longer so that the waves, when they arrive at the screen, are arriving out of phase by half of a wave. In fact, we'll say 180 degrees or pi radians. This means that they destructively interfere and you get cancellation, right? If you make this gap size bigger, right, then the path difference will be larger. Right, automatically the path difference will be larger. So if the gap gets bigger, actually the central fringe, the central bright spot, will get smaller. Right, this is all now way too much to try and think about, and I'm already getting confused myself. But if we just go back to the notes that I selected here, there's a couple of things to remember about single slit diffraction. The central fringe is twice as wide as the outer fringes, so this is twice as wide. Intensity decreases with distance from the center. Yes, they're dropping off. Each of the outer fringes is the same width. These are all the same width here. And they're less intense than the central fringe, but a little bit more. If you use different sources of monochrome light in turn, the greater the wavelength, the wider the fringes. That's something to remember, because this question could have been about changing the wavelength. And this is also important. Using an adjustable slit, the observation shows that making the slit narrower makes the fringes wider. So narrower slit makes wider fringes. Okay, and we kind of talked a bit about why that was. So now let's try and select the correct answer. So we are making the slit narrower, so expecting a wider. So we've got to choose between these two, right? So that's definitely wrong. That's definitely wrong. Okay, now if you make it narrower, less light gets through, so the intensity decreases, so it's going to be C. Okay, I hope you found that one useful. It is quite a tough one. So I've eliminated these two because of this statement here. Right? That's how I eliminated these two. And then I had to choose between what's going to happen to the intensity of the light, and if you make the slit narrow, less light gets through. Okay, next question. Right, next question. So pause the video and read this question. Okay, this is asking us about a narrow slit, diffraction grating. Okay, so this time you've got laser light coming in, you've got this piece of material with tons and tons and tons and tons of lines on there. In fact, 6 times 10 to the 5 lines per meter. And then what you get is you get beams of, it's again due to interference, but you get the 0th order, and then you got the 1st order, 2nd order interference. Right, so you're going to get bright spots, basically a bright spot here, 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 and the 1st order, 2nd order, etc. So it says, which of the following is correct? We know the wavelength of the light, and we know the lines per meter. Well, if we go back to the equation sheet, the diffraction grating equation is this, right? D stands for the separation between the lines. So they've told us the lines per meter. We can't use that. We have to do 1 divided by the lines per meter. Lines per meter. That should say lines per meter. Lines per LM. Lines per meter. This is the angle at which the order occurs. This is the order, and this is the wavelength. So let's go back in and just see what we can do with that formula. D sine theta equals n lambda. Right? So I'll be trying to calculate the angle just to check these out. Okay? So I can rearrange to sine theta equals n lambda over d. Sub in some numbers. So let's try and find the 1st order when that happens. So that will be number 1 for 1st order. That will be times by 490 times 10 to the nanometers minus 9 divided by, right, I can't put in 6 times 10 to the 5, I have to put in 1 divided by 6 times 10 to the 5, right, which actually simplifies down to just inverting this and bringing it up. So I get 1 times 490 times 10 to the minus 9 times 6 times 10 to the 5. So that was the n, that was the lambda, and this is actually Now it's just the number I used for the lines per meter, LM. Alright, so if I calculate that, it will equal sine theta. If I then do shift inverse sine of the value for this, I'll get an answer. Now if I do that, the first time, for the first order, I get 17 degrees. So immediately I could just say, bang, this one is correct. And that's what it's asking for. And that is in fact the correct answer. But, being pedantic, I'm going to go and check the rest. The second order is observed at 34 degrees, so I'm expecting this to be wrong. It's easy enough to do. I can just go in and change that to a 2. What happens? I calculate it, I get 36 degrees. 36 degrees. 36 is not 34, so that doesn't work either. So this one is definitely wrong. The third and higher orders are not produced. Well, this happens at an angle of 17 degrees. This one was 36. If the angle is greater or equal to 90, you won't see it. So let's see what happens at the third order. So all I'm doing again is replacing the number 1 in this equation with 3, calculating it, and I get a value for this time of 61 degrees. So you will get the third order. Okay? Last question. So that one is wrong. Last question. Last thing to think about. A grating with more lines per meter would produce more orders. Right. In order to produce more orders, these values need to be smaller. Right? They need to be closer together, more closely packed. Because once you exceed 90 degrees in angle, you don't see any more orders. So what would happen if I make this number bigger? Which would be more lines per meter. Right? Well, sine 90, if you calculate it, is equal to 1. Right? So essentially, the bigger this number gets, then that means that I'm limited by how big I can make n, because let's just say we made this number really big. Let's just say we made this number 1. Well, then immediately I'm at 1. So I can't even get the first order. So yeah, you can see from the equation that that making this number bigger means that I'm not going to get as many in before I reach 1. Kind of a bit of a bad way of explaining it, but I think you should get the point. If you're not sure, just comment in the comment section. All right. Final question. Pause the video, read the question. Right, this one's actually quite interesting question. It says, which of the following provides direct experimental evidence that light is a transverse wave rather than a longitudinal wave? It's transverse rather than longitudinal. It's not asking which one is proof that light is a wave, because really I think all of these could be used as proof that light is a wave. We're trying to distinguish between transverse and longitudinal. So what I would do here is I'd think, oh well, let's think about sound, right? Sound is definitely a longitudinal wave, right? The oscillations are in the same direction as the wave motion, right? So if this can happen to sound, then it's not proof that light is a transverse wave. So let's have a think. Two light waves that are coherent can be made to interfere. Well, that's true of light. I know it's true. But can it happen to sound? Well, if I get two speakers, I'm using not exactly the best symbol for a speaker, and they play sound, I can get these to interfere with each other. So I could walk along a line here, and I'd hear loud spots and not loud spots if they are both playing the same frequency. It's because of interference. So that's not exclusively proving that it is a transverse wave. Light can be diffracted. Yes, it can. Can sound be diffracted? Yes, it can. Similarly, again, I can play a loudspeaker, add a gap. Well, in fact, this is why, for instance, in a classroom, if I'm shouting in here, rah, right, a kid might hear me round here and go running off, because the sound will diffract out round the corner. So this is not exclusively showing that it is a transverse wave. Light can be polarized. Right, well, can sound be polarized? Sound can't be polarized because, like we showed before, a wave doing this can get through slits like this, but it can't get through slits like this. Whereas a sound wave, which is compressions and rarefications, squashed up bits, more spread out bits, squashed up bits, right, I'm not drawing all the particles, that can get through it either way. So straight away I'm thinking this is the right answer. Whoops, thinking this is the right answer. Let's just go in and check this last one, D. The intensity of light from a point source falls off inversely as the square of the distance from the source. Right, this is true for light, this is true for sound. It's not exclusive, so it's not that one. So the correct answer is C. Okay, I hope you found this video useful. Thanks for watching. Please subscribe, like, and share, and click the bell button so you get notifications.